Okay, so today I'm going to be talking about two things, equilibrium and buffers. And I've already mentioned equilibrium. This should be and. Um, I briefly talked about equilibrium a little bit numerous times throughout the semester. I'm going to talk about it in significantly more depth here. Okay. Wow. Water is not helping at all. Maybe I should go get the bourbon. Oh, God. Okay, equilibrium. First, I want to talk about what goes on in a reaction, and that's going to relate to equilibrium. Okay, so we've got where this is so we're if when we're lower on this chart, the more stable the state is. So we've got all right, where did everything go? There it is. And then we have products. And then we have the energy required to start the reaction. It's called activation energy. That's this hump here. And if we extrapolate over, this stability is going to be in units of energy. We can get the reading on activation energy. Okay, so when we put the energy into the reactants, that splits open the bonds, and we end up with a whole mishmash up here of the atoms from the reactants. So that's called the activated complex. And that's made up of the atoms from the reactants. Now, they're at a very high instability here. So they want to recombine to be more stable. They can do that one of two ways. They can go back to the reactants, or they can go over to the products. And you'll get a mixture of molecules being formed on the reactant side and molecules being formed on the product side. Now, if we look at a time, and it varies per reaction. Sometimes it's very short. Sometimes it takes a long time. For example, the reaction of charcoal and diamonds. That takes a long time to happen to reach this point of equilibrium. So equilibrium now, once we reach this state, is going to be, I'm going to abbreviate that EQ, is when there is no difference between the reactant concentration and product. Now, what do we mean by that? Okay, so we first throw two things together, and immediately, assuming it's like a double replacement reaction, for example, we throw two things together, and all of a sudden we get a white precipitate. Now, so that's the initial time zero. After a while, we keep having this happen. Okay, the activated complex up here will start forming reactants because it's more stable than the activated complex. And, and then it'll be forming products. Both of them more stable than the activated complex. Now, equilibrium, there is something called an equilibrium constant. And the equilibrium constant is when EQ has been reached, like up here, when there's no difference between the reactant and product amounts. Okay, when this happens, when the equilibrium has happened, we have something called a equilibrium constant. That is KEQ. Now, there's a lot of Ks in chemistry. There's Kas, Kbs, KEQs. And again, it's just a matter of those are all equilibrium constants. That's equal to product, let's see, product concentrations over reactant. Remember, square brackets is moles per liter. Okay, so what this means is if this is equal to 1, for example, that means the products the product concentration is equal to the reactant concentration. And anything like 5 over 5 is equal to 1. However, this is kind of a rare thing. Okay, so if KEQ is greater than 1, products are favored. And conversely, if KEQ is less than 1, reactants are favored. Okay, so if it's greater than 1, that means we have more products than reactants. If it's less than 1, we have more reactants than products. Now, if we throw two solutions together and we get a precipitate, and we let it settle down for whatever time it takes to settle down, depending on what's put in what, we're going to reach this equilibrium state. Now, what happens if we adulterate that equilibrium state? Now, this is the part that is called Le Chatelier's principle. Okay, and basically is if an reaction, it's not if and, it's a reaction, if a reaction is perturbed, and what I mean by perturbed means messed with. Okay, at sitting at equilibrium, all of a sudden you throw in something. Okay, the reaction, I need to have lines to draw on here. Let me do one thing here. It's under view. Okay, dogs under my feet here. Okay, if a reaction is perturbed, think of this as changed. Perturbation theory is very, you can take a whole dissertation on perturbation theory. It's pretty cool stuff. But anyway, if a reaction is perturbed, the immediate ratio between reaction and product will change. So what Le Chatelier's principle is, so in other words, KEQ initial is going to be different than KEQ final. So Le Chatelier says that has to not be. So what happens is, so therefore, the reaction will change the ratio of the reactants to products. Meaning the KEQ initial is now equal to KEQ final. So when you change the reaction, now you're going to be doing this in the lab Wednesday, Thursday. So you have a reaction, you let it stabilize, and you're going to get, and you end up with a KEQ or an equilibrium ratio between reactants and products. Okay, these are going to be different, the initial and final. But as soon as we give it some time, the reaction is going to switch back to the initial because the KEQ for that reaction is standard. So that means if we start with 4 moles, let's do a reaction here. Let's go let's not do that. Let's okay, so let's take sodium hydroxide and HCl, acid and base. That's going to give sodium chloride plus water. Okay, so the H and the OH form water. Now this, all reactions have two arrows. And that's because of the activated complex. So we've got a reverse reaction going here and a forward reaction going here. Okay, so now, and we're going to get an equilibrium constant from that, and let's call it 50. And again, let me let's see how I do this here. So that's going to be, this is the products. This is the reactants. Okay, so when we do product over reactants, we're going to equal 50. Now, what if we threw in, now this is at equilibrium now. What if we threw in a bunch of extra sodium hydroxide? In other words, say this was 1-to-1 exactly, and we threw in 3-to-1 sodium hydroxide to 1 part HCl. The product to reactant quotient has to remain at 50. So that means we have to offset this. So in other words, we have to move this around so that the new product these are different, but the ratio means the same. So that's called say we threw in a lot of NaOH. To balance it out, we need more HCl. So where would that come from to balance it out? It would come from over here. And I'm going to redraw this. Water to be like that. So if we add extra sodium hydroxide, we have to come up with hydrochloric acid to balance it off. Where does it come from? It comes from the other side of the equation, from the product side. So we are now going to get one of these to hook up and go this way, which will balance the NaOH. Now in your lab, you're going to be doing quite a few of these just to get practice at it. But this is a theory. You've got to maintain the KEQ. So any change will end up at the new equilibrium point. The ratio will remain the same. In this case, it was 50. So we throw in anything here, and this is going to go back and forth till the new KEQ is equal to the old KEQ. by manipulating ratio in this of product and reactants, so this ratio is maintained. Okay, now if you're in a Chem 400 class, you would spend lots of time on this, what I just talked about, lots. Because the KEQ is a little more complex than just products over reactants. It has to do with, after you balance the equation, it has to do with the coefficients. Okay, so from this diagram here, that's how we end up with this concept of equilibrium, because the activated complex will regenerate reactants, regenerate products. And that's in real time, back and forth, back and forth, back and forth. But the ratio between the products and the reactants will not change. Now that's after equilibrium is reached, though, not before. It can be lopsided, and then it's going to all work its way out. Okay, let's look at this equation again. So instead of, what if we did this? What if we removed some sodium chloride? Okay, now to maintain the KEQ, things have to happen. What's going to happen is, how do we get more sodium chloride on the right here? Well, that's by reacting more of the sodium hydroxide and HCl. That'll regenerate the sodium chloride after it's being removed, because we need to maintain the ratio. So you can add stuff, take away, and the reaction will shift back and forth to maintain that KEQ ratio. Now, on the outside, you usually don't see this happening. You have to have some way of detecting the changes in concentration, either visually or with a piece of equipment like a infrared spectrophotometer or some kind of a piece of equipment. Because sometimes it's not obvious what's going on. Okay, now you've probably never seen this before. So I horrendously simplified this. Because again, if you were in 400, 401, this is drilled into you like, oh my God. Now, this is nice to know in health situations. Biochemistry works this way, exactly the same way. They have equilibrium reached on enzymatic reactions, on non-enzymatic reactions. For example, if we had biochemical reaction where we had a protein and a, oops, let me do that right. What happens is, now this is protease. It's like pepsin enzyme in your stomach. That's an example of a protease enzyme. It hydrolyzes protein. And as you remember, proteins are made up of amino acids. So this is a big long chain of amino acids, usually um, 200 or 300 of them. Okay, so what you yield here is going to be individual amino acids. And this can be like 100, whatever. So, and this reaction has got a KEQ of whatever, let's say 50 again. All right. Our body has something called feedback loops. And one of the feedback loops is we need more AA. So how does the body do that? It does it by increasing the enzyme or increasing the substrate. Substrate is just another word for reactants in biochemistry. And then that'll force more amino acids because we have to keep the equilibrium constant. Now, the one thing in your body, for example, combustion of glucose. Glucose goes through three main cycles. There's glycolysis, Krebs cycle, and oxidative phosphorylation. Okay, those three cycles have tons of feedback loops in them. It's called enzyme regulation, and it all comes down to Le Chatelier's principle. We increase the protein, we have to shift this around. If we increase protein, we've got to end up shifting this around so that more amino acids are made, so that the ratio is 50 to 1 still. There's a ton of reactions. There's another one called the Haber. Haber reaction. Now, Haber was kind of Einstein vintage, and he got a Nobel Prize for this. Dr. Haber, German guy, and he took nitrogen gas plus hydrogen gas and produced NH3 ammonia. Now, the reason why this is such an important reaction is because until they were able to make ammonia for pesticides, for creating a refrigerant, a whole bunch of things, they had to go to the South Sea Islands in South America and harvest bird dung, because bird dung is high in nitrates, and they just used a process for that. So he won a Nobel Prize. And he died a pauper. The reason why he died a pauper, he let the Germans talk him into working for them making tear gas and mustard gas for World War I. So he was, after World War I, he was not a popular guy at all, even though this is very, very, very significant reaction. So they took away his Nobel Prize, and he died literally a pauper. So the way they increase this reaction is they would pull off the NH3 as it was made. So to keep the equilibrium constant the same, more ammonia had to be made so that the ratio was maintained. And this was the trick, using Le Chatelier's principle to minimize NH3 and to maintain that constant of products over reactants. We had to make more of it, so the KEQ number didn't change. So those are two really common reactions, biochemically and non-organic reactions that exemplify Le Chatelier's principle. So if one part of the reaction is stressed, the reaction will move back and forth to minimize the stress. So Le Chatelier, what he does is to maintain the equilibrium constant, will shift to the right or left. 2 to maintain that constant. So it's a very powerful concept. And until you get the knack of this, it's kind of hard to put your arms around this. Um, so that's equilibrium. Are you guys okay with this? Now you'd have to really go over this a fair amount. Um, so that this becomes reasonable. Okay, so are there any questions? I know that it's hard to ask questions when you've just been introduced to this. Okay, so let's talk about buffers. Um, Now, what is a buffer? Okay, this is an acid-base situation. Okay, a buffer will maintain a given pH. So let's say we had a 4 pH buffer. Now remember, the buffer will do things to keep the pH at 4 because it's a 4 pH buffer. So if we add in acid, adding in the acid will reduce the pH. If we add in a base, it'll raise the pH. So that's how it maintains the pH 4. Let me give you a common buffer situation. Let's look at baking soda. Okay. Um, Baking soda is used in our bodies to maintain blood pH. Now, blood pH in our bodies is extremely important. The reason for that is enzymes are designed by nature to work at an optimal pH. So, for example, going back to protease, that's in our stomach. Okay, that's an acid environment with a pH of around 2. Okay, if we change the pH of our stomach to, let's say, neutral, the protease enzyme will not work very well at all, if at all. So our body goes through all these ways to maintain in our stomach pH of 2. Now the problem is physiological pH is 7.04-ish, which is very neutral. So when our stomach contents are emptied into the small intestine, our bodies have to neutralize that acid from the stomach, so that the other enzymes are designed to work at pH of 7, which will work properly. One of them is lipase, which digests fats, another is amylase, which digests carbohydrates. So it depends on the structure of the buffer itself. Now, let me show you how baking soda works. Okay, so we've got actually it's okay. So if we were to throw in a um a base, for example. Okay, the OH, now when we throw in an OH, the pH should go up. Okay, so how does that buffer keep it from going up. The way it keeps it from going up is to neutralize the OH. What's the easiest way to neutralize the OH is with an H. So the buffer kicks on an H, and you end up with water. So the pH doesn't go up, it stays, because we've mitigated the OH, the hydroxyl ion. Okay, well, what about acidic conditions? Okay, so we throw in H plus. What happens then is the H plus is absorbed into this, so we end up with that. So again, it neutralizes by absorbing it in and replacing the sodium hydroxide, it forms H3PO4. So it doesn't matter which one you throw in, the sodium hydroxide will somehow deal with it. And dealing with it is how it buffers. It neutralizes the onset. If you throw in OHs, we're going to neutralize it with an H. If you throw in an H, we're going to neutralize it by absorbing the H into the H2PO4 forming H3PO4. So that's the way of the buffer. And there are slick ways to design a buffer. Say you wanted to design a buffer to buffer at, say, pH 9. You're going to have to change this guy. This is the buffer molecule. So you have to change that out because each buffer molecule neutralizes differently. Some are favored on the alkaline side, high pHs, other are centered on the lower side. Now in lab, Wednesday, Thursday, you're going to be mixing and playing around with different buffering solutions. But the concept is this. It has to neutralize either way by definition. If it doesn't neutralize either way, it's not buffering. Okay. So I want you to have a little introduction before lab next week, or the latter part of this week, on what equilibrium means, what buffering means. Okay. How do you guys feel about buffers? I think they're easier than equilibrium, but another thing going on with my cough is I'm thirsty all day. I can't drink enough water. You do not believe how much water I drink. And it doesn't. So something's going on in my body that's screwing things up. And I eat very plain food, except when I go out to restaurants. But normally I eat at home. Um, you know, um, like today, I'm going to have a toasted cheese sandwich with an ear of corn. I mean, just real simple, not spicy. Anyway, so I don't know why I'm always thirsty. Okay. So,
What time are we meeting for lab today?
well, I said in the email 6 o'clock. Why don't we meet earlier than that? Like, because I'm still at home. And most of you probably are at home also. Um, is 5:30 doable?
5:30 is perfect.
Yeah, I can try to make it by 5:30. I'm on the other side. I'm in North Sacramento, but yes, I'm sure I can make it over there.
Okay. I'm going to put out a note regarding that. Okay. So yeah, 5:30. Now the rest of the week, let me talk about that. I want to focus on projects and a combination of study skills. Okay, because we've got tomorrow's going to be the practice test or test 2. And then Thursday's the test, and then Monday we have kind of an open class, and that'll be a time you can bring in your projects. The finals on the 29th, and the 30th, I'll be in for projects, if any of you want to bring your, haven't done your project presentation on that Thursday, the 30th. And then we're done for the semester. Okay, grades are due by October 11th, and you won't be able to get them on a transfer, uh, get them transferred to another school by the 12th. So on the 12th, your transcripts will be updated. And that's a very big deal for professors, when grades are due. They are really punitive if you don't get your grades in on time. The vice president of instruction calls the dean, the vice president of instruction calls the dean. The dean wants to know why their grades aren't in, and the dean calls the professor, wants to know what's going on. So it's a big deal. However, I don't turn in my grades till the very last day. The reason for that is Canvas changes. So I wait long so that Canvas will get a chance to stabilize. If I submit grades too early, then I have to change them. And it's it's a pain to change them. Okay, anyway, so the 12th, your transcripts will be available, updated, and all your classes you're taking over the summer, probably just one. And then next week, I want to give full attention to studying for the final on Monday, getting all your projects turned in by Thursday. And then tomorrow, we're going to go over the practice tests for Thursday. Okay. And then one other thing, I don't know if you guys caught on, but my finals are made up from prior tests. So the best way to study for my final is to go over the practice tests 1 and 2. So that Tuesday before we can go over any problems on either one of those tests over. Okay. My coughing is returning here. So I'm going to sign out. Any other questions? Okay, so let's